In the 6th chapter of this course on locational marginal pricing, we will be discussing microeconomics. First, we'll start with some nomenclature, specialize that to an example of apartment rental. That will lead us to market clearing price and surplus. And then we will discuss longer term issues. In the case of apartments, that means the construction of new apartments. In our electricity market context, that means new generation expansion. We'll also look at operating costs, cover the very important case for an electricity market of inelastic demand, discuss spot and forward markets, and then there are a couple of homework exercises at the end. First, nomenclature. We're going to need to discuss the functional relationship between demand and prices in a market. In contrast to the sciences and engineering, in economics, it's standard to graph price on the vertical axis of a graph, where the price is being considered to be the dependent or the independent variable. Economics also refers to a demand function as a function with price as its argument, in other words, the independent variable, and quantity demanded or bought or rented, as the case may be, as the dependent variable. The inverse demand function is a function. It may not exist, but if it exists, it has quantity demanded as its argument, in other words, as the independent variable, and willingness to pay as its dependent variable. The phrase demand curve is used to refer to either or both of these relations without being explicit about whether price or quantity is the independent variable. So whereas in engineering we tend to graph the independent variable on the horizontal axis, in economics we plot price on the vertical axis, irrespective of whether we're thinking of it as the independent or dependent variable. Similarly, the supply curve shows the relationship between supply and prices. Supply function has price as its argument and quantity as the dependent variable. And the inverse supply function, or offer function, we'll generally refer to it as offer function, is a function with quantity produced as its argument and the required price as its dependent variable. Again, to refer to both of them, we'll say supply curve. We actually first discussed the offer function in the context of electricity markets in section 5.3.4. Again, another difference in the convention in economics to engineering is to use the symbols P, lowercase or uppercase, for price, and Q for quantity. There's obviously potential for confusion in power systems if we use that convention. So what we're going to do is use lowercase pi to refer to price, X for decision variables generally, and P, whether lowercase or uppercase, for the real power, and Q for the reactive power. So for economists, please be aware that we're not using the standard economics symbols. We'll first consider an example that is somewhat familiar, apartment rental. And then we're going to generalize various aspects of that example to apply to an electricity market. So let's consider that we've got some renters in a geographical area who are interested in renting an apartment. And we're going to ask them, each of them, their willingness to pay. What do we mean by willingness to pay? It's the amount of money up to which they're prepared to pay to rent an apartment. And we're going to graph that reservation price versus the number of apartments, ordered from highest to lowest reservation price. So using our nomenclature, the demand curve shows the number of renters willing to rent, in other words, the quantity, for a given price. And by the way, if I'm willing to pay $1,000 per month, then I'd be happy to rent at any price at or below $1,000 per month. In this case, we could think of 1,000 as the reservation price because it's something I want to buy. It's my maximum price. I'm going to draw from one of the textbooks or reference books for this course, Intermediate Microeconomics by Varian, and the next figure is going to show figure 6. Based on figure 1.1 of Varian's book. So for future reference, I'm also going to define a thing called the benefit. and in this case it's really the benefit per unit time, to be the sum over the renters who actually get to rent apartments of their willingness to pay. So here's my demand curve. You can see that at a price of $500 per month, there's actually only one renter willing to rent at that price. At $490 per month, however, the first renter is happy to pay that price, and there's another renter who's prepared to pay $490. For prices from there down to $470, down to just above $470, there's still only two, but once the price is at or below $470, there are at least three renters, and so on. That graph applies when there's only a few renters, but when there's a large number of renters, we can think of the demand curve as being a continuous curve. So both the demand function and the inverse demand function exists. When we generalize to continuous value consumption, which is applicable in electricity, we'll think of the benefit as being the integral of the willingness to pay over the range of consumed goods. We're also going to assume that there are arbitrarily many potential renters so that the curve extends arbitrarily far to the right. That may not be a reasonable assumption in electricity, for example. So here's a continuous demand curve. And again, this is based on Varian's book, Intermediate Economics. Now let's suppose we have a number of landlords, and let's suppose there's a total of them. I'll write S overline for that number. I'll use overline typically to mean the maximum possible. So indeed we could think of S overline as the maximum possible apartments that could be rented. And they're going to rent identical apartments, this is an idealization, on a month-to-month basis. In the short run, the number of apartments is not going to change. The maximum number is not going to change. So we could think of the supply as being inflexible, or in economics, the word that is used is inelastic. That is to say, the total number of apartments for rent stays fixed despite variations in price. For now, we're going to assume that there are no operating costs of leasing an apartment. We'll bring that in later on in this chapter. Of course, it's very relevant when we want to discuss electricity because there are operating costs of generating power. So the question we might ask is, at what price or prices would these landlords rent? Let's think about a few hypothetical situations. If any two apartments were renting at different prices, there's two people, let's say, one's paying a higher price, one's paying a lower price. Well, the person paying the higher price would have an incentive to cut a deal with the owner of the lower priced apartment to rent at some intermediate price. What can we conclude from that? If any rental prices are different, then some landlord and renter want to change the rental arrangements to their mutual benefit. What this means is that all prices paid by the renters must tend towards a fixed number that's the same for everyone. So let's define a concept that helps us to explain that sort of situation. In the equilibrium, which we define to be where there's no group of renters and landlords who could change their situation for mutual benefit, all the prices paid by the renters will be the same. So it's important to understand that this arises because of individual interactions between renters and landlords. We don't have any centralized coordination, but the price in the market for apartments will tend towards an equilibrium price that's uniform across all apartments. Furthermore, let's imagine that a landlord faces some price. We've just argued that it'll be the same for all landlords. Let's suppose that price is pi, and let's presume it's greater than 0. If the landlord doesn't rent, then his operating profit or her operating profit is 0. Operating profit means the revenue minus the operating costs. Our operating costs are 0, so in this case, if I don't rent, I don't incur any operating costs, but I don't get paid, so my operating profit is zero. On the other hand, if the landlord does rent the apartment, then the operating profit is pi per apartment times one apartment. So what's a landlord going to do? Clearly, each and every landlord is going to rent out their apartment if the price is positive. So if all prices are greater than zero, all S overline apartments are going to be rented. Conversely, if the supply of apartments rented is S overline, then any positive price could occur. Figure 6.3, which is again based on a variant figure, shows the story by representing the supply as a vertical line that represents the number of apartments. The supply function exists, but strictly speaking, the inverse supply function doesn't exist in this case, but we have a supply curve. So now the question is, if we have a supply of S overline, which renters will actually rent? Which price, what allocation of apartments to renters would result in no one wanting to change their situation? By definition, this is the equilibrium price and quantity. So let's just consider a possible candidate. Consider the intersection of the demand curve, which we drew earlier, and the vertical line representing the number of apartments, in other words, the supply curve. The intersection defines a price. Let me write that price to be pi star at the quantity x equal S overline. What is the significance of that price? Well, indeed, it will be the price that the renters will pay. Let's have a look at it. Here's the intersection of the supply curve and the demand curve. It occurs at a price pi star, and of course corresponding to supply S overline. We've already argued that there will be a single price in the market that every renter is going to pay. I claim that that price is pi star. Let's see why that is. Well, if it's not pi star, then either it's above pi star or below pi star. So let's suppose that the single price is above pi star. In that case, only the people whose willingness to pay is at least pi, and remember, by assumption that's above pi star, will want to rent. So that means there'll be less than S overline apartments rented. Some of the apartments will be rented, but not all of them. So one of the landlords of the unrented apartment, who's not making anything, not renting his apartment, and therefore his profit is zero, would presumably offer to lease at a cheaper price than pi to capture one of the renters, to grab one of the renters who would otherwise pay price pi. So this means we're not in equilibrium. Conversely, let's suppose that the single price is below pi star. But in this case, more than S overline renters would want to rent. In fact, we could only rent S overline apartments because that's all we have. There would be some unsatisfied renters. Their willingness to pay would be more than the price pi. And so they'd be willing to pay more than pi to capture one of the apartments. Again, we can't be in equilibrium. So if every price above pi star is not in equilibrium and every price below pi star is not in equilibrium, then the only possible price is P star, and indeed at that price no renter wants to change their situation. Because any renter has a valuation, a willingness to pay at or above pi star, so they're happy to pay pi star. Every renter who is not renting has a willingness to pay below pi star, and so therefore is not interested in paying pi star. That price is very important. It's called the market clearing price. It's the price that equates supply to demand. So clearing here means to make supply equated to demand. And at this price, to summarize, neither the renters, the potential renters, in other words, the ones who are not renting, nor the landlords have any desire to change their situation. Furthermore, the renters having the highest willingness to pay get to rent the apartments. Summed across the renters, if we add up their willingness to pay, which remember we call their benefit, actually their benefit per unit time, per month, if they're on a monthly lease, is maximized. The benefit minus the operating costs, remember in this example the operating cost zero, but the benefit minus the operating costs is called the surplus or sometimes the welfare. We'll mostly refer to it as the surplus. We're going to consider non-zero operating costs later in section 6.5. At the market clearing price, pi star, surplus is maximized. And by the way, that price is the same as the Lagrange multiplier on supply-demand balance if we formulated an equality constraint problem of maximizing benefit minus operating costs subject to supply equaling demand. This is also going to be true in the case of non-zero operating costs. Furthermore, if our sensitivity analysis from Theorem 4.11 applies, the market clearing price pi star is the sensitivity of surplus to changes in supply or demand. And in this context, it's sometimes called the marginal surplus. The price pi gives the right incentive for actions by individual renters and individual landlords to maximize the surplus. We could imagine a centralized implementation. A central agent, for example, could announce this price. If they did, then the actions of individual renters, individual landlords in response would result in maximizing the surplus. For future reference, we can divide the surplus into consumer surplus, which is the benefit minus the total paid by the renters, and producer surplus, which is the total paid by the renters to the landlords. How about some longer-term issues? In the longer term, if the price was sufficiently high, then new investors might decide to build new apartments, or in the case of our electricity system, new generating stations. If the price pi star is high enough to support the investment, new apartments would be built. That's the supply side. How about on the demand side? Well, in the longer term, there might be more potential renters. This would tend to increase the equilibrium price compared to the case when there were less renters, all other things being equal. But if we had a potential for new investment, that would tend to decrease the price again. So the amount of new entry, the new equilibrium price, depends on the relationship between the willingness to pay of new renters, the construction costs of new apartments. So far we've ignored operating costs. But let's think about what would happen if there were operating costs of renting the apartments. So let's say, for the sake of argument, that apartment 1 has operating costs C1 of $150 a month. Apartment 2 has a higher operating cost, $155 per month, and so on. So in this case, instead of a vertical supply curve, the supply curve would equal C1 at a supply of 1 apartment, C2 at a supply of 2 apartments, and so on. There'll still typically be an intersection of demand and supply, but let's suppose C high was pretty high and it was above the highest willingness to pay of the renters. That's not the case for this example, but if it were, there would be no intersection. So let's assume there's an intersection. Then at the intersection, the difference between the benefit of renting the apartments minus the cost of supplying the apartments is still maximized. That is to say, the market clearing price at the intersection maximizes the surplus. Of course, the reason why we're looking at this is because in electricity markets there are also operating costs. Here I've drawn a case where there are operating costs, and instead of a supply curve at 60, in order to get up to 60, we need to incur operating costs. Again, there'll be some intersection of demand and supply, but typically at a different quantity and price compared to the previous intersection that ignored operating costs. Again, we can divide the surplus into consumer surplus, the benefit minus the total paid by the consumers to the producers, and the producer surplus, or the operating profit, which is the total paid to the producers minus the operating cost of production. In electricity, operating costs are primarily due to the cost of fuel, and we've already discussed that in the context of economic dispatch. As a general rule, new generators of a particular type of technology tend to have higher efficiency than old generators. So if we ignore changes in fuels and fuel costs, in the long term, the supply curve tends to shift down to lower prices as new capacity is introduced and occasionally old capacity is retired. Of course, changes in fuels and in fuel costs could either reinforce that effect or they could act in opposition. In electricity markets, we need to face a particular characteristic that is not very common and not very commonly thought of in other markets. The issue is that the demand may not change much with price. We say that the demand is inelastic. There are several reasons for this inelasticity. For example, the consumers may not care about price. Their willingness to pay for electricity may be far higher than the price. Some consumers, and this is particularly the case, at least historically, for residential retail prices, they may not be exposed to wholesale prices or may not be exposed directly to wholesale prices, at least as they change in real time. So in this case, instead of a demand curve that slopes downward, meaning with greater quantities the prices and willingness to pay would be lower, the demand curve is vertical. There will still usually be an intersection of supply and demand. However, in extreme weather conditions, in the context of electricity, there may be no apparent intersection of supply and demand. And a key question in that case is, what is the appropriate rule for setting the price? We really need to revisit this issue in the context of electricity markets, specifically in the context of defining the value of lost load. So here's a case where the demand curve is vertical. Instead of gently sloping down as my previous examples, it's vertical. There's still, in this case, an intersection of supply and demand, but that may not always be the case. The description so far has really been relevant to a spot market. There are producers, in our case these were landlords, consumers, in our case these were renters, who interact to trade. In electricity, this is called a real-time market. The actual price, the quantity traded, will depend on the interaction between supply and demand at the time of trading. It's uncertain until that time. In advance, it's uncertain. In a forward contract or futures contract, the parties decide on a manner of trade in advance, a quantity and a price that enables them to commit to a contracted quantity at a fixed price, which avoids the variability of the uncertain spot price for that quantity. And the deviation of the actual from the contracted quantity is still sold at the spot price. In electricity, we'll see that the day-ahead market is a forward market. There are also other futures and forward trading in advance even of the day-ahead market. Such futures and forward trading is especially important in electricity because the real-time prices are very variable. We say they are volatile. By locking in those prices, at least for an agreed quantity, future and forward trading helps with investment, as well as helping to avoid exposure to the volatile prices. If we imagine investors or a bank thinking about building or investing in the construction of a new generator, they might require evidence that the investment will be repaid. The forward contract provides more certainty than spot prices because we have a contractual agreement with someone who has an interest in consuming the energy. So in this chapter, we looked at an example of apartment rental. We looked at renters, supply, equilibrium, market clearing price, longer-term issues, operating costs, inelastic demand, spot and forward markets. It's based on Varian's book and also a little on Kirschen and Stribic. In the next chapter, we'll apply some of these ideas to electricity markets.